Welcome you all to the Applied Mechanics seminar series. We have a little bit of delay in starting today because of some glitch in the YouTube connection. Professor Science this evening we have with us Professor Alok Sinha from the Pennsylvania State University. He is from Mechanical Engineering Department. He's a professor there. He has joined recently our Applied Mechanics department as an adjunct professor. Professor Alok needs probably no introduction for people who work in this area of rotor dynamics and dynamics of structures. But still, for others, I will give a little bit of introduction to Professor Alok. Professor Alok is currently with the Mechanical Engineering Department, as I said, of Pennsylvania State University. He received his BTech from IIT Delhi and PhD from Carnegie Mellon University. He has made extensive contributions in the area of vibrations, rotor dynamics, and control systems. His other areas of interest are in robotics, neural engineering, and to name a few. He has published extensively in these areas of research. He has also published a few textbooks on linear systems, as well as vibrations of mechanical systems, and most importantly, vibrations of periodic structures. He is a fellow of American Society of Mechanical Engineers, American Association for Advancement of Sciences, and Associate Fellow of AIAA. Professor Alok is going to give a talk on vibrations of bladed rotor with geometric mistuning. It's reduced order modeling and system identification. I'll give the presentation to Professor Alok. Thank you.
Thank you. So I can share, right?
Yes, I'll unshare and you can share. Yes.
Okay. Okay, everybody can see my screen?
Yes, it's on, yeah.
Yeah, good. Okay, thank you, Sheikh and Farooq and Sayan for arranging this seminar. So I'm very happy to be part of IIT Madras. So without any delay, my seminar topic is vibration of a bladed rotor with geometric mistuning, and I'll talk about specifically reduced order modeling and system identification. So as you can see in this jet engine pictures, this bladed rotor refers to fans, rotor stages of compressor and turbine, and geometric mistuning specifically refers to integrally bladed rotor, or so-called BLISK. So where it's a single piece of casting consisting of both the disc and the blade, and then the blade geometries are obtained by milling machine, which introduces variation in geometry from blade to blade. Okay.
Professor Alok, is it possible to go full screen?
Yeah, sure. That's what I'm looking at. Is it better?
Yeah, it's visible. Yes, thank you.
Yeah. Okay, so what do we really mean by mistuning? So bladed rotors are periodic structure. So you have here is an academic rotor with 24 blade-like structure. So this is called a periodic structure, okay? So there are as many sectors as number of blades, and this is periodic because these sectors are basically repeated n times, where n is the number of blades to form the whole bladed disc. And so therefore, computationally, I can just model just one sector and obtain all the dynamic characteristic like natural frequencies, mode shapes of the full bladed disk assembly. So that is very computationally efficient. But because of inevitable small variation in blade to blade properties, which is called mistuning, cyclic symmetry breaks down, and then sector analysis is no longer applicable. So also this problem is stochastic in nature. These variations are random, right? So just modeling one rotor is not enough. You have to think in terms of probability distribution of amplitude. What is the probability that amplitude exceeds certain critical value? So therefore, we have to develop high fidelity reduced order model. And that's one of the main topic of the presentation. So here is just before I start, I want to discuss some basic characteristic of rotationally periodic structure. So here is the most basic model of a bladed disc, where each blade is represented by one mode of vibration, represented by modal mass Mi and modal stiffness Ki, and Kc is the coupling stiffness. So as I've shown in this dotted box, that is one sector, okay, in this case. And this sector is repeated n times, where n is the number of blades to form the whole 360-degree bladed disc. Now, in this case, since the sector is single degree of freedom system, if all blades, all masses are and modal stiffness are identical, I can come up with a single degree of freedom model, irrespective of the number of blades. And if you look at the stiffness matrix, this has, particularly for perfectly tuned system, if you look at the structure, this is a cyclic or circulant matrix. Each row of this matrix can be obtained by simple shift by one slot of the previous row, and that is a reflection of cyclic symmetry. So even though this model is simple, even when we do the finite element analysis of the full rotor, these structure of the model retains. Here the delta K is a diagonal matrix, is a scalar, and delta M, there is a change in mass matrix and stiffness matrix due to mistuning. So these structures have this important characteristic. If I look at the eigenvalues and eigenvectors of a perfectly tuned system, in this simple model, I can come up with a closed form expression of eigenvalues. So the point here is that there are repeated eigenvalues, and it is n minus 1 over 2 for odd number of blades, and n minus 2 over 2 are even number of blades. And these repeated eigenvalues define the characteristic of a bladed rotor, okay? And so the eigenvectors turns out to contain constant interblade phase angles. So there are n interblade phase angle possible, where it is integral multiple of 2 pi over n. So if I look at this case for n equals 3, so there are 3 modes, all blades having same phase and same amplitude, and then there is 120-degree interblade phase angle and 240-degree phase angle. And it so happens that if you look at the 120-degree interblade phase angle and 240-degree interblade phase angle, these modes correspond to the same frequency. You can see there is a forward traveling wave and backward traveling wave, and the structure doesn't see any difference. And there are repeated eigenvalues. And so in odd case, the 0-degree interblade, that 0-degree interblade phase angle is the only corresponds to unrepeated eigenvalue. For even number, you have interblade phase angle 0-degree, 90, 180, and 270. 90 and 270-degree interblade phase angle mode shape, they correspond to the same frequencies. And here 0-degree and 180-degree interblade phase angle mode shapes correspond to unrepeated eigenvalues. Okay. All right. So when eigenvectors are repeated, eigenvalues are repeated, then eigenvectors are not unique, right? So because any linear combination of those two eigenvector corresponding to repeated eigenvalues are also an eigenvector. So in perfectly tuned system, there is no unique eigenvector, but moment it is mistuned, these repeated eigenvalues split, and there are unique eigenvectors. And not only that, when the modes are close together, like you can see the nodal diameter map, which is basically a natural frequencies versus the interplayed phase angles known as harmonic index. There are many frequencies close together. So there is, once it gets mistuned, then there are a lot of modal interaction. And that can lead to vibration or mode localization. So here you have example of mode localization. It's a very small change in the thickness of blade, and you can have one mode where only one blade is basically vibrating, and that's a mode localization. Okay, and that is kind of shows all the problem due to mistuning, because all the energy is concentrated in one blade. One blade will have large amount of vibration and it can break. However, in gas turbine application, it's the force response which is important, because there are always non-uniform pressure field circumferentially, and and when the blade is rotating, it automatically leads to periodic excitation. And then if you do the Fourier series expansion, there are integral multiples of rotor speed, which turns out to be possible excitation frequencies. But for resonance in this structure, two conditions have to be satisfied. First of all, natural frequencies has to equal integral multiples, one of the integral multiples of rotor speed. Secondly, associated mode shape. So where this natural frequency, there is a resonance or frequency matching, then associated mode shape must be contained in a spatial variation of pressure field. Otherwise, energy will not get transmitted to that mode for a perfectly tuned system. So this is what is very important from for a forced response point of view, which is present in a gas turbine engine. There are two issues. A lot of people in the literature, they say vibration mode localization. But if there is a mode localization, that is mode shapes are localized, it does not necessarily mean that forced response will be localized. So there are two different mechanics. that we have to be aware of. So if we look at the force response, and in a very simple way, if I look at the transfer function, that is from the response of a blade to the excitation in a particular engine order excitation or particular interblade phase angle. In this case, the transfer function will have a numerator and denominator. For a perfectly tuned system, numerators are all equal, and there are many pole zero cancellation, because this denominator will be essentially 2nth order, right? It's it's n mass, so it'll number of eigenvalues will be 2n. But there are many pole zero cancellation for a perfectly tuned system, and essentially it behaves like a single mode, single degree of freedom system. Okay, but moment is mistuned. Those numerators are not equal, and there are no pole zero cancellation, and transfer function become of order 2n, and energy can get transferred to many modes, and many modes get excited, and that can result in one blade having maybe 2 or 3 times as much vibratory amplitude as other blades. And here are examples of pole zero cancellation for a tuned system. Only the poles, single pole, complex conjugate poles become effective, and it acts like a second order system, where a mistuned system, there are no pole zero cancellation. So order of the system increases, and the energy can get transferred to many modes. So that is the mechanism. So now let me get back to the geometric mistuning. So this is an example of integrally bladed rotor or blisk, and it is chosen because it's aerodynamically efficient. There are reduced number of parts which are very favorable, but it has very low damping in the system, and there are blade to blade geometry variation. So when there is a lower amount of damping, then this mistuning effect or vibration localization due to mistuning is even a bigger problem. Okay. And another disadvantage is damage in one blade may lead to replacement of the whole IBR. So that's the integrally bladed disc. And so how do we develop the reduced order model for that? So in this example, there have been many research. So in mistuning, I think the first paper occurred around 60s, early 60s. So almost 60 years of research on mistuning has been going on. And more recently, last 3 decades, many efforts have been made to develop a reduced order model. But all these efforts is focused on modeling the mistuning by change in the frequency alone. And that is, mode shape change in blade was neglected, and it seems like it worked very well for many systems. So just like, what is frequency mistuning? So if I have, so we represent mistuning by change in Young's modulus of blades. So we have a nominal thickness geometry B naught for a blade, and if this blade thickness changes by some amount, so its geometry is changing, then what we do is that find the natural frequency of this blade, and then we revert back to the same thickness of the blade, but we change the Young's modulus of this blade to match the frequency of the mistuned blade. Okay, so this is what is the frequency mistuning, and based on that, S&M technique has been developed to develop the reduced order model. Quite simply, in this case, the mass matrix, there is no mistuning in mass matrix, just the stiffness matrix, which is denoted as K frequency, and then we choose certain number of modes of the tuned system, which is represented by matrix phi naught. So that becomes my approximation. That is, y is the modal coordinate. And then I can come up with the reduced order mass matrix and reduced order stiffness matrix. Okay. So when this method was applied to geometric mistuning, people were not able to get a good reduced order model. Okay, so it was very frustrating to many researchers because any mistuned mode is a linear combination of all the tuned modes. Okay, because tuned modes are a complete set of eigenvectors. So people were wondering why it is not working, because in S&M or frequency mistuning, you are trying to represent a mistuned mode as a linear combination of tuned modes. But the problem here is that we do not want to take all the tuned modes, right? So idea was to consider tuned modes, only those tuned modes which are in the frequency range of interest. So that thing was not working when there is geometric mistuning, which leads to simultaneous and dependent perturbations in both mass and stiffness matrices. So I came up with a new approach, which I am calling Modified Modal Domain Analysis. And essentially, modal domain analysis was, it required large number of modes. And because of geometric mistuning, we needed to move in the vertical direction, orthogonal direction. And that's what this MMDA does. Okay. So this MMDA is based on proper POD, proper orthogonal decomposition of coordinate measurement machine data on blades geometries, and we only uses the sector analysis using ANSYS and a solid modeling model. Okay. So this is an example of a POD feature. This is based on actual CMM data. So we have the coordinate measurement machine, and then we do the similar value decomposition, and I can get a POD feature. So here, these color bar indicates the magnitude of the geometry change. Okay, so that's one of the POD feature. Okay, so in this MMDA, the modification is that in my basis vectors, we have phi1, which was in the original reduction, that is R tuned modes with blades having average geometry. In addition to that, I created more basis vectors, and they are R tuned modes with Phi-L are tuned modes with blades having perturbed geometry along the POD feature or mode that I want to consider. So the NP is the number of POD modes that I am considering. So these are, the geometry is perturbed, but again, all blades are perturbed by the same amount. So I can still do the sector analysis, because that's important, because industrial scale bladed disk FEM finite element models have millions of nodes. Okay, so we really we want to avoid the full rotor analysis. And then we have this reduced order model where I have a reduced order mass matrix and reduced order stiffness matrix. Okay. So these are the sector analysis which will be required by MMDA. So for the average geometry, we do the sector analysis for each nodal diameter. And then we also do sector analysis for nodal diameter corresponding to 180 degree or 0 degree interblade phase angle blades. And here I do this for each mistuned IBR blades, and then I subtract it from the mass matrix and stiffness matrix of average blade to get the delta M and delta K due to mistuning. And then I also do sector analysis for each nodal diameter where blades are average geometry plus perturbation along a POD feature. So these are the data that we have to generate using ANSYS. So I'm going to present an example for an integrally bladed rotor with industrial scale integrally bladed rotor and an actual coordinate measurement machine data. So it's a full rotor model is it has number of nodes is 166,068. And so for each sector, you can see the reduction in the number of equations for each sector versus full rotor. And there are 18 blades. Okay. And so how do I calculate the POD feature? So if I do the spatial coordinates of the ith node, okay, and then I rearrange all the spatial coordinate of all nodes in a blade in a column vector. So this is for lth blade, one blade, and then I can calculate the mean over all the 18 blades, and then I calculate the deviation in blade nodal coordinate geometry. And then I stack them up. First column is for delta W matrix. First column, delta W1 is for first blade, delta W2 is for second blade, and delta W18 is for 18th blade. And then I do the singular value decomposition. And then POD features are the column vectors of this matrix U1, and weights of POD features, the singular values are the sigma, and here it is plotted for this so-called Purdue rotor POD. So we have, you can see the similar values, and so first few features are more important in representation of geometric mistuning, but even this smaller features, they are not dying out and they are still there, although small. And then I go through this creation of all the data for implementing MMDA. And these are some of the POD features for an example. So this color, if it is red, it means large geometry changes. So this is first POD, second POD, fourth POD. Okay, so just to give an example. And that's the nodal diameter map. So this is like we have a family of nodes. This is for average blade tuned system. So you can see it's 18 blades. So there are repeated eigenvalues. So 0 means 0 degree interblade phase angle. So that frequency is unrepeated. And also the 180 degree phase angle, which is the last value, and since it's an even number of blades, is again corresponds to unrepeated eigenvalues. But all others are actually, there is a single point, but they are repeated eigenfrequencies. So 1, 2, 3, 4, 5, 6, 7, 8. 8 are repeated. So 8 times 2 is 16, and 2 unrepeated 18. Okay. And so there are different family of modes. If you look at it, the first family is first bending mode. I think second is the torsion modes, or so depending on the nature of modes of the blade, you can classify them. Okay. So here is the MMDA. So we have delta M, delta K, we can get delta, all these delta M, these are block diagonal now, matrices. I can get them by doing actual mass minus tuned mass matrix, and also actual stiffness minus tuned stiffness. And we have, let's see, phi 0 is set of tuned modes of system with blades having the mean geometry, and then sets phi L is phi L is set of tuned modes of system with blades having perturbed geometry along the POD number of POD features that I want to use. And then you have a reduced order matrix, MR and KR. So we have these algorithms developed to do this calculation in an efficient way. So we can get the reduced order matrix, and then I can solve the eigenvalue problem with KR and MR, which is of much reduced order, of considerably reduced dimension. So here are the result. If I look at the MAC, so I also do we have also done the full 360-degree analysis, just for the sake of comparison as to how good the reduced order model is. So actual mode, when I say, that is coming from the full 360-degree ANSYS analysis. Okay, so if I just take only the average blade, you can see the MAC of the, they are far away from each other. MAC has to be 1 for exact match of the mode shapes. And as I increase the number of POD features, the results are getting better. And here are the results. Well, when I have at least all the 15 POD features, things are looking very good. And when I consider all the POD features, the reduced order model looks good, almost exact here. And that was not the case for the frequency mistuning modeling. And here are the frequency deviation. Okay. Are there any questions or?
Yeah, Pankaj, can you mute yourself?
Okay, so shall I just continue? Are you listening? Everything going all? Technology working okay?
Yes, Professor Alok, you can continue. You can have question answer session at the end of the presentation.
Okay, good. Okay, so we have this frequency deviation with respect to tuned frequency. And again, as I am increasing the number of POD features in the reduced order model, results are getting better. Actual means result from the full 360-degree ANSYS analysis, and with the 17 POD, it matches the actual frequency deviation very well. Now, here are the results from FMM and SNM. So those are the approach, reduced order model approach using frequency mistuning. You can see large error here in frequency. So here I am using error D, which is frequency deviation error. So you can see how I have calculating this. Now, in the literature, most of the previous papers use this measure. Error is frequency ROM, reduced order model, and minus frequency actual over frequency actual by 100. Okay. Now, this measure gives misleading result. I will give you an example. Suppose frequency ROM is 102 hertz, frequency tuned is 98 hertz, and frequency actual is 100 hertz. So if I use this model, it will tell me, or this measure, it will tell me that I have only made 2% error, which is misleading, because here you want to show how good you are in capturing the deviation in frequencies from the tune system. So if you do error D %, which I have defined, so I'm trying to predict 2 hertz change, but my reduced order model says 4 hertz. So that will mean 100% error, right? So in that measure, FMM and SNM do not do good. And this measure also says that when you are not able to predict frequency deviation, you will not be able to predict the mode shapes. Okay. And now this good match is shown by using the very stringent, very tough measure like error frequency deviation percentage error. Okay, so that shows that frequency mistuning is not adequate to model geometric mistuning. Okay, and here are the mode shape comparison from frequency mistuning approach, so-called SNM and FMM, and you can see MAC are not. SNM takes more number of modes, is better, but is still far from being perfect. FMM is totally off. Okay. And here are the forced response based on reduced order model. So this also shows you the effect of mistuning. See, so this blue line is the tune system response. As I said earlier, that for tune system, energy just goes into one mode, and you can see that this behavior is like a single mode resonance, right? Now, moment it becomes mistuned, energy gets into many modes, and there are multiple peaks. And if you look at the ANSYS, when I say ANSYS, it is full 360-degree analysis. Okay, so there is two harmonic response depending on the resonant frequency that I am using. And you can see there can be amplification of amplitude by a factor of 2, right? And again, the frequency mistuning approach does not predict the force response well, whereas the MMDA results are very close to the full 360-degree analysis. Okay, so next I'm going to talk about system ID. Is there a time limit? How much time I have? 15 minutes, 20?
Yeah, you can go ahead with another 15 minutes, no problem.
Yeah, okay. So this is system identification for using blade tip timing data. So we want to predict the vibratory behavior of blades at the design stage. So we have 4 components to do this. We want to have a good model of the mass matrix, stiffness matrix, damping matrix, and the forcing function. So we can claim that MMDA provides a high fidelity reduced order model. So we have a good model for mass matrix and stiffness matrix, provided we know the geometric mistuning. That is, we have the CMM data available. And damping matrix and forcing function still cannot be accurately computed in spite of advancement in CFD techniques. And when blade geometries are not easily measured, then there is a need to estimate blade alone natural frequencies and mode shape. So to estimate mistuned natural frequency of each blade, many techniques have been developed with the assumption that forcing functions are known, which can be valid for traveling wave type excitation commonly used in laboratory setting. So first of all, we developed algorithm for identification of forcing function from measured vibration data. So the approach is to represent the sinusoidal forcing function as a solution of second order differential equation. So we can convert the force estimation problem as a state estimation problem, for which we have used Kalman filter. And however, here we have assumed that there is no modeling error. Model is perfect. And we published 2 papers, and one of the key findings is that Kalman filter approach is very robust to measurement errors. So I'm going to talk briefly about simultaneous identification of mistuning, damping, and forcing function from vibration data. And so here I'm going to use unscented. We have used unscented Kalman filter, and it has been shown to be highly successful for nonlinear system in many applications. Okay. So that's the model of unscented Kalman filter. You have a state equation which is nonlinear in general, and then you have a measurement equation yk, and you have measurement noise and the process noise represented as white noise. And then this is a picture for how this estimation process works. So we have a sigma points, and based on the actual nonlinear equation, there is no linearization involved. We create the statistics of the states before the measurement is taken, and based on these statistics, I can determine this so-called Kalman filter gain K. Yeah. And I after the measurement comes, I modify my estimate. So that's the way it works. And we applied it to our simple spring mass model, and we are going to do simultaneous identification of mass and of the damping, forcing function, and mistuning. Okay. So first we assume that forcing function is known. So we are going to estimate damping and mistuning, and we are using the steady state response. So here we can see that we have 2 times n algebraic equation, and we have 2 times n unknowns, n mistuning parameters, mistuning stiffness, and n damping. So in theory, we can do it, but we don't use the direct approach because it is very sensitive to error. So we are using unscented Kalman filter here. And you can see my state becomes x dot, and then gamma and delta k. So we have equations that gamma is, gamma dot is 0, and it becomes a state equation, and delta K dot is 0. That's another state equation. And those becomes, so I'm doing the state estimation here. And here are the excitation, known excitation, sinusoidal excitation with the L equals 2. So engine order excitation for is a 10 blade. So interblade phase angle will be 2 pi over 10, 36 degree. Okay, and these are some of the measured response with noise and everything. That's the result that's the response we are using to get the damping coefficients, and it predicts very good results. So here are the red line is the actual value, and the algorithm is giving good identified damping coefficients. And similarly, it identifies the mistuning very well. Okay, and there are results are for 2 level of noise. So now with unknown forcing function, now we have this equation u dot plus omega square u equals 0. So u is the unknown forcing function. So I have augmented my state space model. So I have 2 additional states u and u dot. Now, in this case, there are 3 NT unknowns, gamma I, delta Ki, and U0I. And we have only 2 NT algebraic equation if I use the steady state response. So when we use the steady state response to do this identification, simultaneous identification of damping, mistuning, and forcing, it was not working, and we realized that steady state response does not have sufficient information. So therefore, we use the transient response, that response before it settles into steady state, and we show. So this is the data that we use, measure data, transient response, and we find that results are pretty good. Again, the damping coefficients, unknown forcing, we are getting very good result. Mistuning, we are able to do the identification very well. And this is the estimation of forcing function. So this is delta F1 is the error. So it should be 0 ideally. Okay, and so it looks like it's not working that well. But when I look at the Fourier coefficients, results look very good. So if I look at the Fourier coefficients, so since it's a second engine order excitation, we know that's what we have provided. Then for that, only second and 10th coefficient should be 0.5, and other should be 0. And when I look at that measure, indeed, the results look very good. So we are able to identify the unknown forcing function. So we have 2 different approach. When forcing function is known, and so we can do mistuning and damping. But we can use the steady state vibration. But when forcing function is not known, we must use transient vibratory data. And we have also applied it to frictionally damped case. So there are friction dampers in gas turbine to reduce the resonant vibratory amplitude, but it makes the system non-linear. And this is a single mode of vibration with a frictionally damped system. And if the forcing function is sinusoidal, then the response can be sinusoidal with the hysteretic loop. And so we have used the Newmark method for integration, and which is which is a standard method for structural dynamics. And in this case, we have this, my state vector has the friction force, FDK, and the slip load, mu n. Okay, so we are trying to identify these quantities. And the unscented Kalman filter is able to identify the friction force and the slip load, which was actual value was 1, quite well. And then we have extended it to the unknown forcing function. So there are two additional states, FEK and FEK dot for the unknown forcing function. And again, we have to use the transient vibration data, and we get a very good result for this case. Okay. So we can estimate the forcing function, friction force, and the slip load. So in conclusion, we have presented MMDA and as an accurate reduced order model of a bladed rotor with geometric mistuning. Unscented Kalman filter has been successfully used to identify mistuning, damping, and forcing function from measured vibration data. And we have extended it to frictionally damped blades by integrating Newmark method and UKF. Okay, so any questions? Now I think I will stop here and take any questions you have.
Thank you, Professor Alok. If you have any question, you can unmute yourself or put up your hand, and then I will allow you to ask a question. Or you can put it in the chat. I think Professor Alok can read it from there and answer the question. So, Professor Sain Gupta.
Okay, before I do, I want to show one more thing. Okay, I want to share one more thing. Okay, can you see my screen?
Yes, Professor Alok.
Okay, so this is the cover page of my book that was published in 2017, Vibration of Nearly Periodic Structure and Mistuned Bladed Rotors. And this picture that is a so-called academic rotor I have used a lot in testing the new algorithm. So I put this picture on my cover page. And then I realized that it has 24 blades, and the Ashok chakra also has 24 spokes, right? So it's a great coincidence that my cover page is a representation of Ashok chakra, okay, which is the Indian emblem. Okay, thank you.
Yeah, Professor Sain.
Farooq, I think there are, let us have questions from others. I think Vidyarish once has some 3 questions. Let him first go through the course with the questions.
Good evening,
Okay,
sir. This is Vidyarish here from GTRE. I have 2-3 questions. One is the average blade in the analysis considered for that 18 number of blades, BLISK, is the average of 18 mistuned blades, not the theoretical blade. Why so? That was
Yeah, it is average of the 18 blades we have chosen.
So 18 blades considered in that analysis, not the theoretical average blade.
Not the theory. Yeah. In this, we have taken the actual measured blades.
Yes,
and we
because
took
if the deviations are very high, then we'll be deviating from the average blade. That's what I was curious to know, why that way it is considered.
If the deviations are very high,
on those 18 blades, the average blade considered itself will be a very highly deviated blade.
That's right. And the deviation we capture by including the POD features.
Yes, sir. That's the second question I was coming. Now we are if we are going to start a new design itself, that time we'll not be having the 3D CMM coordinate data. We may be having the legacy data. So in that case, what should be the sample size and how we can come out with this POD features for a ab initio new design? This is applicable. What we have explained is for a already tested or measured data on
Yeah.
manufactured blade. In the absence of such a data for a new design, how can we go about it? It's provided we have the limitations on the tolerances of the blades from hub to tip. We know what kind of variations can come. Can we use that data and generate the POD features, or we need to have this measured data? Because when we start a new design, we'll not be having the CMM data, and this mistuned analysis is required at the beginning of the design rather than after finalization.
Yeah, good.
So
Yeah, I think, yeah, that's true. I understand your question. So if you have no information on mistuning, then you can define what kind of manufacturing process you want to achieve. Secondly, if you know the manufacturing process, right? So in one of our first paper, there were a lot of data available for a rotor blades for a manufacturing process. So we divided that data into two parts, and that was chronological, okay? And we tried to see whether the POD features in the second set of data that we generate are contained in the first set of data, which turned out to be true. So yeah, so if you don't have any knowledge of the manufacturing process, then this approach can be used to define your manufacturing process, like how much tolerance
exactly, sir.
you
That is the
can
intention
tolerate.
with which I asked this question.
Beg your pardon?
Exactly with the same intention I asked the question, because if we have a set of data of our old data, we can imply and see whether the mistuned rotor blade which is going to come out within those tolerances is acceptable by design or not. So in that perspective,
Yeah, we have done some studies, and it seemed like that study showed that it is possible. So we had a lot of data. So I divided into two parts, and it was chronological. Okay.
Sir, another question is the number of blade sectors define the number of POD features we are going to generate from that matrix once we do the single variable decomposition. If you consider all the POD features, the matrix size is not going to reduce. So how do we decide which POD feature, how many POD features we need to have in the matrix?
Yeah, I think POD feature, if we consider, it is reduced, but not by as much. Still, it is reduced. Like I had to do a 17 POD. So it so happens that when we first applied this to academic rotor, we didn't have to take many POD features. But for the actual data, as you saw, we had to take almost all POD features. That came as a surprise to us. Okay. So yeah, so that is there. That probably we can get away with less number of POD feature in some case, but that need not be the case. Another thing which was very surprising, that since we have to do a lot of to generate these features, POD features and associated mode shapes, we have to do a lot of ANSYS analysis, and that's very time consuming. So we developed a perturbation scheme, like if we just know the POD feature, can we just estimate the mode shapes by perturbation analysis? So that worked very well for this academic rotor, but it has not worked well for the actual industrial scale rotor. So there I have to generate all the mode say basis functions by new ANSYS analysis, which is time consuming. But when we had to do Monte Carlo simulation, what we found that if I look at the various permutation of those 18 blades for which I have already conducted the ANSYS analysis, so doing the permutation does not require much effort. That gave almost the same statistics if I was going to do Monte Carlo simulation in a very traditional way, in which every time I change the blade, I have to do the sector analysis for the ANSYS. Okay, so those are some of the result I can share with, but it was to our surprise that we had to take almost all the POD features, even though some of them were quite small.
Thank you, sir.
Yeah, great questions.
Thank Vidya. Anyone else?
Farooq, can I ask some questions?
Yes, please. I think there is one more question by Dilip who has written it on the chat.
Yeah, yeah.
If you can see that.
I'm not able to see the chat. Can you read it to me?
Yeah. Dilip asked that total damping consists of material friction and friction damping, aerodynamic damping. Is it possible to separate contribution from each?
We have not done that. Okay, I will leave it to that. It may be possible, but I have not given much thought to it yet.
Thank you. Professor Sinha?
Yeah. Thank you, Professor Sinha, for a very nice talk, and it was quite interesting to listen to this. I have one question. When you are using this frictional damping in your model, so essentially when you have this frictional damping, the system becomes sort of non-linear. Because you have this state, it becomes non-smooth. The system becomes non-smooth.
Yeah.
So I understand what you did in terms of the state estimation, but if that frictional damping is there in my original model, can we still use this MMDA approach?
If there is a non-linear so MMDA only works, we only have a linear case, mass matrix, stiffness matrix. But if I have, this is again, I have not given thought. That could be a good future work. What happens to if there are nonlinear stiffness, right? If a cubic stiffness and other things, whether when we have a basis function, whether I can get by with a subset of tuned modes, right, in the certain frequency range. I guess you can always represent any response as a combination of tuned modes. The only question is how many. So here we are able to, like, say, I want to look at resonant frequencies around, say, 1000 hertz. Then I pick up the modes near 1000 hertz and I can develop reduced order model. But if there is nonlinearity, whether that is possible or not, that might depend on case by case basis.
Yeah, because it will actually depend on it would be difficult to we can always linearize it, but the problem in such systems would be that we won't know the switching or manifold or switching point
Yeah,
in the
yeah,
so that would be the challenge in my opinion.
yeah, yeah, definitely. Yeah. There are some work done on reduced order model with nonlinearity. Okay, so yeah, it will be worth looking at it and
that
see whether
the
we can develop a high fidelity reduced order model in the presence of nonlinearity.
Yeah, I was asking in the when you were doing this using this Kalman filter based approach for this estimating, uh, essentially you are, as I understood, you are now treating the uncertain parameters as additional state variables, so the state
Right,
dimension increases further.
right, right.
So you are doing this Kalman filter basic in the original state space, or you are doing it in the some transformed or some
Yeah,
reduced state space?
augmented state space.
So augmented
Yeah,
state space is bigger than the
bigger than the original one, right?
so the
So even
computational
for a
costs
linear
would,
system,
yes,
parameters, unknown parameters makes it a nonlinear system.
correct.
Yeah.
So you the computational costs are what was the it was quite high or it was reasonable?
Yeah, I think it was reasonable, and there are two issues whether we want to do real time or offline. So offline, of course, is no problem. If you have the tip timing data collected and you want to do the identification, that's not an issue. But if you want to do real time diagnostics or identification, then computational time will be important. Uh, yeah, yeah. I think that's something that we have to be, careful about whether
Yeah,
we can apply
yeah.
in real time or not.
The second point is that when the moment you are using Kalman filter based approach in any of this identification, so
Mhm.
essentially you are doing some sort of a linearization in some locally.
No, that is the difference between unscented Kalman filter and other filter. Unscented Kalman filter does not use any linearization. It uses the actual nonlinear equation. See, linearization, that's known as extended Kalman filter. And that was, so those were not working for many nonlinear systems. Yeah.
Okay.
So we use actual nonlinear case, the nonlinear equation, no linearization in unscented Kalman filter.
And the last question is just a clarification that when you are using the MMDA approach to get the deviatoric matrices, so that would mean that you would still need the FE modeling of all the mistuned blades, right?
Yeah.
Okay, and then you're just subtracting K minus delta, K minus K dash and M minus
Yeah.
M dash. Okay.
Yeah, in that we don't have to do the eigenvalue analysis. We just have to form mass and stiffness matrix and do the subtraction.
So
That's how we got it.
yeah, if you don't
Now,
need to do the eigenvalue, then I think it's substantial savings in computational costs.
right, yeah. And we have also looked at it, once you have the POD feature, can we generate the result by perturbation analysis? It has worked well for academic rotor, but for the actual rotor, it has not worked well.
Okay, thank you very much, Professor Sinha.
Welcome.
Farooq,
Thank you.
yeah, Farooq, I am done.
And thanks. And I think there is one more question we can take. I think Resma has a question. Resma, can you please unmute and ask?
Yeah. Hello, sir. This is Yashma here.
Yeah.
Sir, I have a question regarding your approach. Can the same approach be used equally for bladed discs and BLISK? Because bladed
Yes.
disc have the
Yes,
Hello?
it can be used. Yeah.
Sir, in case of bladed disc, we have additional element like Sayan sir was talking about the friction damping coming into picture. In that case,
Yeah.
the response variation will be there because of the damping difference between the blades. How that portion will be covered in this? Because while formulating, we have not considered the damping variations, right? And that too, at the design level, we won't have information about it.
Yes, that is true. So if you have a damping variation, we can try to modify this to include. Now there is an issue. There is damping, mistuning in damping. Can it be? Can it lead to, vibration localization?
Yes, sir.
I think that's an open problem. So I guess the thing is that if you define what your problem is or how you want to modify or extend this is possible. We may not be able to apply it exactly the way it is, but we can come up with a solution.
So we may need to do some modification to this approach if you want to use it for the bladed disc systems.
When you want to
If
model
I-
the damping variation.
Yeah, because bladed disc system will have the damping variation between the blades. So there we will need to modify this, right?
Yeah, so currently what we do, the damping is being modeled. Once we have the reduced order model, then we inject currently modal damping, right? So those modal damping
Yes, sir.
can be different in different modes.
Yes.
So that can be done because there's nothing, once we have the reduced order mass matrix and stiffness matrix, right? And we use proportional damping. That is a typical approach. Now, another thing is if damping is not proportional, is it proportional? Then the what do you call, the mode decoupling is not possible, right?
Yes, sir.
So those are other issues that the modes can get coupled because if the damping is non-proportional. So do you use proportional damping or non-proportional damping?
So normally we also take proportional damping only.
Exactly.
But
yeah.
we
So,
are not, it depends on the advanced level of simulation which we are doing. We may want to include the other way.
So right now, the way we calculated forced response, like I showed you for the integrally bladed rotor,
Yes.
we took 0.1% damping in each mode.
Yes.
Okay. So that's the way we have simulated. But if you have a different damping, we can inject into that, right? You can even inject non-proportional damping. It's just that you have to do the inversion of the full matrix to calculate the response.
Sir, I have one more question. Like, what's your viewpoint on the disk stiffness in this whole scenario? Like, if the disk is flexible or the disk is stiff, the scenario what we are seeing here will see a major change or it will be similar? When we are dealing with the disk which is flimsy and flexible and the disk which is stiff.
Yeah. So in general, the vibration localization depends on the coupling stiffness. When it is small, then there are papers which says that mode-like localization, not the forced vibration localization, that is more likely to happen when it is a very flexible disk. But other extreme, when you have if you have very high stiffness, coupling stiffness. So essentially, again, you have many frequencies close together, right? So,
Yes, sir.
so my take on it is that all the results are case by case basis, and there is some guideline as to a smaller coupling with smaller damping leads to more mistuning problem, but it is case by case. I don't think there is any general theory regarding that.
Okay, sir. Thank you very much, sir.
Thanks, Resma. I think Shankar has a question. Shankar?
Yeah, good morning, Professor Shankar here.
Good morning.
The lecture was very good. It covered the entire spectrum. So for the paucity of time, I think I will only ask a few clarifications. I think later we can take it up. The first one is about the mode localization aspect, what you talked about with respect to the forcing function. So in that scenario, what's the order that we need to consider in the blade basic profile? When I say order, what is the sampling size that we should have to capture such localizations which needs to take place?
Sample size meaning? Can you?
The number of points that it should be available on a given profile for us to take a given POD.
Oh, you mean when you are doing simulation, how many frequencies you want to check?
One is on the frequencies, Professor, and another one is on the to generate a reduced order model, we should have sufficient degrees of freedom to capture it. So I'm talking about the degrees of freedom part.
Okay. Let's see. Yeah, I'm just trying to.
Yes.
Yeah, so, right?
Yes.
So essentially, like say I want to, my resonant frequency that I am worried about is in this band, let's say 4.5 or 5 or something, right? So normally we take 10-20% all the modes around that frequency.
Okay. Okay.
Yeah.
Yeah. Then, Professor, with
that was the success of MMDA. We can get away with a small band, all the modes. Whereas if we didn't have MMDA, it was not working.
Okay, I think there are going to be challenges if otherwise the size of the models are going to be bigger. We will be getting into other coupling issues, which will be starting from the other modes.
That's true. And then there are some veering regions, and also there is more model interactions in the neighborhood, you know. So yeah. So we have to choose that band.
Okay. Professor, with respect to the data which is being used to identify the system identification part, which you covered at the end, when you talk about NSMS data or a tip timing data, what is the basic data that we are considering in this case? Is it the time of arrival we are going to take it up, or it is the displacements? What is the information that needs to be used?
I think it's the displacement, the vibration. I think there is a processing once you get the tip timing data.
Okay.
And you can predict the vibration, right? Blade vibration.
Okay. That means when you say a transient, in that case, you talked about a transient response, but mostly we are talking about a synchronous response, which is going to be with respect to a specific order of excitation. In that case, mostly we will be expecting a steady state, isn't it? Then the transient portion, if you can explain a little further, it will be helpful.
Yeah, transient means that if you, before it settles into a steady state, if you have the data, can we generate those data?
So it is something like a blade pass, which takes place in a given passage? Is it that is the transient we are talking about?
Yeah, you can say that.
Okay.
Yes, that is before it settles into steady state. If you can generate those data,
Yeah.
and then we can identify a known forcing function and mistuning simultaneously.
Okay. And one last question on the POD part of it. So when we are talking about a given set of a rotor, which you have the information available with you, is it the way that we need to go towards the, for a specific mode, we can understand the variations, or we should go towards evaluating a POD, then the effect of the POD on those modes? What is the approach that should be taken forward?
Yeah, if the CMM data are available, then we can find the sensitivity of a POD feature to the force response.
Even if it's for a modal domain, if you want to really look at only the effect of that on the frequencies, then how that we should look at? For a given mode, we can look at, or for a given POD, what is the effect of on the other modes?
Yeah. So we have looked at some blade alone frequencies that we are able to predict very well from the POD feature.
Okay, and that is applied across
numerically computing the sensitivity, and we calculated the frequencies of the blade without conducting any new FEM, and it matched well with the experimental result. Blade alone.
Okay, in that case, what my colleague Reshma was asking about the flexibility, the disk flexibility does not play a major role. Can we take it that way?
No, disk flexibility, because when it comes to the bladed disk, we are having all sort of problems in the integrally bladed rotor. So that effect is due to flexibility of the disk, coupling between blades. So mistuning is really a factor because of the coupling between the blades, because of the flexibility of the disk.
Thank you, Professor. I think we will be having a long interaction later. I think I'll.
Yeah, please.
Mr. T.N. Suresh would like to have
further discussion with you.
Yes, sure, sir. Mr. T.N. Suresh would like to have a small clarification. Professor Faruqi, Mr. Suresh is joining with me.
Okay, yeah.
Professor, thanks for your nice lecture. We heard a lot
Thank
about you, and now today for the first time I heard you. But you heard over a discussion like this. What I want to ask is, we know the mistuning and its control and response due to a forced excitation is amenable to a lot of computation and calculation and all that. When it comes to mistuning as a way of controlling the flutter responses and controlling the flutter as a phenomena itself, how much of computations are amenable and how much of computational work is done to control the flutter by design? That's what I would like to know.
Yeah, I think there are a lot of work available in the literature on mistuning. In general, the feeling or the general rule of thumb is mistuning helps in flutter and bad for forced response. So there are a lot of work available with CFD and everything. Yeah.
That means it's amenable. Even the people have designed a priori even before a manufacturer, before a design is frozen, and people have done the studies to fine tune.
Yes, like there are engine companies done. If I can send you a couple of papers to start off with. Yeah. I have worked on friction damping of flutter myself. That is, most of the problem is friction damping is for resonant stress. Actually, that was my doctoral thesis, friction damping of flutter in gas turbine engines.
Thanks, Professor. Thanks a lot.
Yeah, thank you. Yeah.
Thank you, Suresh. It's already half an hour for question and answer session, I think, discussion. So I will ask one more question that is Pankaj has asked here. He has asked that how can we include the effect of blade bending and sap torsion during blade mistuning investigations?
Oh, this is the blade. All the modes are in FEM. They are all captured. So, like say for example, first bending mode. So if I like FMM or considers only one family of modes, so that will be first bending mode. So these, like in this nodal diameter map, all those modes are included. So it's already there in the FEM. Did I answer your question?
Yeah, so Pankaj, it's that the ANSYS model or the finite element model will capture all the effects to bending and torsion. Is that Professor Alok?
Yeah.
Yeah, and I think Vidyadesh has one more small question. So with that, I will finish. So Vidyadesh has asked that can the flow excitation be considered in MMDA model?
Which flow excitation?
Vidyadesh, can you unmute and say which flow
I
excitation
need
are
to
talking
say
about?
the excitation from the flow.
Yeah, of course.
That flow field, can
Yeah.
it be
So,
applied as a forcing function in the model?
yes, we have already done this. A typical approach is that you decompose it into many modes, those interblade phase angle modes. So any excitation can be decomposed into a Fourier series expansion and or in those spatial modes. So we take one mode at a time because when we know the resonance, that's what captures. All modes don't excite. So yes, we do.
But would that mean that, this is subject to the condition that we are not considering fluid structure interaction type of forcing, right? Because then it would become nonlinear.
That is one of the things that when I say damping matrix and the external forcing, when I'm trying to identify, those are coming from those fluid structure interaction. Although which is very hard to model, but we can make an attempt to identify them from the measured vibration data.
Okay, thank you, Professor.
Yeah, thank you, Professor Alok. I think we will not take any more question. Professor Stein, do you want to do the closer?
Yes, it was absolutely a pleasure to have Professor Sinha with us today, and I think we learned a lot today. And now that we have him as officially in an official status with respect to IIT Madras, I think we will have more and more such interactions and we look forward to these interactions. And Professor Sinha has also agreed to conduct a short-term course also that we will sometime plan according to the
Yeah.
Yes, and we look forward to an exciting journey in front of us.
Yes. I'm also looking forward to my interaction with IIT Madras, GTRE, and all of you. It's a great pleasure giving a talk like this.
Yeah, thank you, Professor Alok. Thank you, everyone. Thanks, Sayan, and good evening to all of you. And let us finish it here. Okay. Thank you.
Thank you.
Bye.
Thank you.
Thank you. Bye.
Thank you.
Thank you, Professor. Thank you.